Hello, my name is Laura Seay, and today I will be discussing the research topic, does geographic location play a role in horse racetrack deaths? Sorry, getting something out of the way there. When discussing geographic location, precipitation and temperature are two environmental variables that come to mind. Precipitation in both liquid and solid forms affect the ground on which the racing occurs. Each horse races differently depending on the firmness of the ground. Temperature, both high and low, can also affect the racing abilities of the horses. As with any creature, horses become acclimated to their location and can be affected by temperature changes. For this project, racetrack fatality data was collected from the American Jockey Club's Equine Injury Database. Since 2009, this database has reported yearly racing injuries, which are bound to the time frame of injuries reported within 72 hours after the completion of the race. Deaths that occur after 72 hours are assumed to be caused by other means. Out of the 114 racetracks listed in the database, 25 provided almost complete records for the years 2009 through 2020. This smaller number of racetracks was used in this analysis. The number of race days per month was collected from the Equibase website. This website lists all races that occurred each day and their results. Monthly summarized precipitation, snowfall, and temperature data was collected from the National Oceanic and Atmospheric Administration's National Weather Service for the 25 racetracks. All values are from historical records for the years specified for this study, so 2009 through 2020. Precipitation and snowfall are reported in inches, while temperature is reported in Fahrenheit. To get the data ready for analysis, the racetrack fatality, temperature, precipitation, and snowfall data were entered into Excel files, converted to CSV format, converted to point shape files, and projected using each racetrack's UTM coordinate system. The data conversion from CSV to shapefile and the subsequent projection and regression analysis efforts were performed using Esri's ArcPro GIS software package. The number of fatalities per month is a calculation based off the yearly death value and the number of races per month for each racetrack. A monthly rate was needed for better analysis with the monthly environmental data. For each racetrack, the monthly fatality rate was estimated by dividing the total yearly death value by the total yearly number of race days. This value was then multiplied by the number of race days per month. This calculation was done for every racetrack in this study. This calculation does introduce risk due to the possibility of misrepresenting the actual monthly data, but it was necessary for this analysis. This is a map of the racetracks used for this research project. Racetracks span the entire United States, but are concentrated in California and the Northeast. When comparing the raw fatality numbers to the numbers of race days per year, the East Coast tracks consistently reported over 55% of the fatalities each year. This is most likely due to over 50% of the races taking place on the East Coast. The remaining fatalities and races are almost evenly split between the racetracks on the West Coast and those located in the middle of the country. For example, in 2010, the East Coast tracks contained 65% of all the fatalities and held 57% of all the races. For that same year, the West Coast had 18% of the fatalities and 23% of the races, and the Mid-States had 17% of the fatalities and 21% of the races. The main statistical analysis was performed using the generalized linear regression toolset within Esri's ArcPro software. This type of analysis was used because it models how a dependent variable relates to one or more explanatory variables. The tool provides 3 possible regression model types to evaluate the relationships. If the dependent variable is a wide range of values, the continuous model type would be best to use. For dependent variables with only 2 possible values, the binary model type would be best to use. And the best approach for this study was to use the count model type, which is used if the dependent variable is a discrete value and represents specific events. For the study, the dependent variable is fatality rate per month, and the explanatory variables are precipitation, snowfall, and temperature. Each explanatory variable was modeled individually and then combined into all possible groupings. So precipitation and snowfall, temperature and precipitation, temperature and snowfall, and finally temperature, precipitation, and snowfall. If a location did not receive snowfall, the individual snowfall model and any combinations containing snowfall were not run. The regression model will not actually execute when the explanatory variable is 0. For this analysis, it was assumed that all explanatory variables would not be significant and the coefficients would be 0, meaning they would not influence the dependent variable. The results generated after a regression model run contains coefficients, probability values, and the corrected Akaike information criterion, or AICC. The AICC is used to compare the fit of the different models. The model with the smallest value is the best fit for the data set. The p-value is the probability of the coefficients being 0, meaning not influential. The null hypothesis for this value is that the explanatory variable is not significant to this model. If the p-value is below your significance value, for example, 0.05 for a 95% confidence level, then the explanatory variable can be identified as statistically significant. To signify significance, the variable is marked with an asterisk next to the p-value in the result table. The coefficient symbolizes the type and strength of relationship between the dependent and explanatory variables. If the coefficient is a negative number, the relationship between the variables is negative. In other words, if the explanatory variable is high, the dependent variable would be low. If the coefficient is a positive number, the relationship is classified as positive. In other words, if the explanatory variable is high, the dependent variable would also be high. For this study, coefficients with a p-value below 0.05 were statistically significant at the 95% confidence level. Some general takeaways from the regression analysis. The model runs containing only temperature registered the most significant p-values along with the smallest AICC values, making these the best model fits overall. In contrast, precipitation was the worst model fit due to its consistently higher AICC values. Snowfall had the largest negative coefficients, and in general, snowfall's significance changed either negatively or positively when combined with temperature versus when snowfall was run by itself. Models containing snowfall displayed more significant values than those models without snowfall. And when reviewing all possible explanatory variable combinations, the most significant combination was the models containing all three explanatory variables. And in those combinations, temperature was usually the most significant out of the three. Here is an example of the regression results for Belmont Racetrack in New York. This type of data was produced for all racetracks within the study. This particular model run contains all three explanatory variables and has the second best AICC value out of the 7 model runs for Belmont. The p-values for both temperature and snowfall are significant. Temperature has a positive coefficient and snowfall has a negative coefficient. This means as the temperature rises, so does the change in racing deaths, the chance of racing deaths. Also, as snowfall increases, the chance of racing deaths decrease. This decrease is most likely due to the racetracks postponing races due to inclement weather. No racing means no racing deaths. This next model run for the Belmont Racetrack contains 2 explanatory variables and has the best AICC value out of the 7 model runs for this racetrack. As with the last example, the p-values for both temperature and snowfall are significant. Temperature has a positive coefficient and snowfall has a negative coefficient. And the same as the last results, this means as temperature rises, so does the chance of racing deaths. Also, as snowfall increases, the chance of racing deaths decrease, and that's most likely due to the racetrack postponing races due to inclement weather. This model run contains precipitation and snowfall, where only snowfall was identified as significant. Snowfall's coefficient in this run was much more negative than compared to the last 2 sets of results, which were around negative 0.7, which may signify that snowfall is less significant when combined with temperature than when combined with precipitation. And finally, when snowfall was run individually, the p-value and coefficient are almost the same as the previous model run containing precipitation and snowfall. This could mean that precipitation has no effect on the significance of snowfall. This type of analysis, the type of analysis presented in these last 4 slides was done for each of the 25 racetracks to look for patterns in the data that would help with determining if geographic location truly could make a difference in racetrack deaths. In conclusion, it can be argued that in general, temperature may influence racetrack fatalities, meaning as temperatures increase, racetrack fatalities may increase as well. Snowfall may influence racetrack fatalities, meaning as the amount of snowfall increases, the amount of racetrack fatalities decrease, which is most likely due to racetracks postponing races when snowfall amounts are high. Precipitation provided the least significant values and could be said that it's not significant to this study. And the next steps in the analysis would be more precise evaluation. Each death would be analyzed separately, and the analysis would be done on a day-to-day level versus a month-to-month. Thank you for your time, and are there any questions?